this video will cover the second part of section 6.1, which is looking at Euler's method. I know it looks like Euler's method, but it is pronounced Euler's method. So in the first part of section 6.1, we looked at slope fields in order to sketch a graph of a curve of a differential equation that we couldn't find the equation for y. So that's just looking at a graphical representation. You couldn't really estimate values of points there or anything. So for Euler's method, what this allows us to do is take a numerical approach. So it's kind of a basic idea behind slope fields in kind of finding a rough sketch of the curve, but it gives us a little bit more information in that we can actually evaluate points if we wanted to. All right, so let's talk about, first of all, a linear approximation of a curve. So let's say that this is actually the same exact example that we started off with slope fields. We have a differential equation dy dx equals x plus y, which we've already talked about. I cannot solve for y here. So I could create a slope field and sketch a curve going through the point that they want me at 0, 1. But I can also kind of estimate here using polynomial graphs that we know of. So let's say that this is a solution curve here. So let's say if you solved for y and you called that f of x, let's say that is the solution curve there. And it looks actually, if you look back at the first example in the last set of notes, you'll see it's a very similar curve there from 0 to 1. So now, what I mean by a linear approximation is if we know that we have the point 0, 1, we know that. We know that the graph goes through that point. And we find the tangent line, because if we have the point and we have the equation for the slope, then we can create the tangent line, which is this line here, which we say L for linear approximation. Okay, so if I know that the slope is x plus y for this example, and my x is 0 and my y is 1, that means the curve has a slope of 1 at the point 0, 1, like we already said. So if I were to write a linear approximation, that's just using the tangent line. So that's going to be, we have a y-intercept of 1 with a slope of 1, so that's just y equals x plus 1. So that's what this line is here, line x plus 1. And I can actually use that because very, very close to 1, it's pretty on, or very close to what the curve looks like. So what Euler came up with, he wanted to improve on this approximation. And actually, I haven't even approximated yet. So let's say if I wanted to approximate that using my linear approximation, I would say that y at, we're approximating. If I were to approximate this at, let's say, 1, then you would say, if I wanted to know, like, what this, if I wanted to know what this point right here was, okay, then I could approximate it, and I could find this point right here. Now, we have a bit of a gap, we have a bit of an error here, but we could approximate it, okay, be closer than just randomly looking at the graph. So if I wanted to approximate this, we would say that's L of 1, which would be 1 plus 1, which is 2. Okay, so we could evaluate that, and so right here, that has a y value of 2, and we can see it's a little bit above that, but it's close. Okay. Okay, so what Euler did is he said he could improve upon this approximation by proceeding only a short distance along this tangent line and then changing direction. Okay, so if you look at the second example, we have what I'll call L1. We'll call this L1 right here. So this line is the same line as our L in the first example. We'll call that the first linear approximation. Okay, and then halfway to 1, we change direction. So at point 5, I now am creating a new kind of like a tangent line. And so what I do is I approximate what is the y value at this point. Okay, because that's less of an error than if I evaluated at 1. So if I find the y value at that point, and then calculate the slope of my line at that point, I can create a new tangent line. All right, so, and what this kind of step size is called, we call that a step size, and we label that h, we denote it h. So instead of stepping all the way to 1, we can step half of that and go to 0.5. And obviously, if I stepped half of that at 0.25, then I'd get an even better approximation. Okay, so I want to find a new linear approximation. We'll call that L2. So we're going to call this line here L2. So I need a point and a slope. So I know at 0.5, I don't know the exact point on my curve, but I can estimate that point on that curve by using L1. So we're going to say L1 at 0.5 would be, L1 was x plus 1, so that would be 1.5. Okay, so that y value is 1.5, which is an approximation of what the actual curve is. And then I can actually find out what this slope is of the curve. So I'm going to calculate dy dx at the point 0.5 and 1.5, which again is approximation. So and that is, remember, x plus y, so that would be slope of 2. Okay. So line 1, it had a slope of 1, and now I'm looking at line 2, and it's actually now a slope of 2. So we have a new approximation, which is going to be y minus my y value equals slope times x minus my x value. And let's go ahead and solve that for y. So we get 2x plus 0.5 is our new equation, and that is the equation for L2. Okay, so our new approximation. So now, if I were to use this new approximation, all right, and I wanted to figure out what our function was at 1, we'd actually have less of an error than we had if we had just used the first equation. So in our first equation, we evaluated the value to be at 2. But now if I use my new equation, we could say L of 2 at 1 is equal to 2 plus 0.5. So we're getting closer with the value of 2.5. Okay? All right, so let's just go ahead, and if I were to change direction again, let's say if I wanted to continue following this curve and find other values like at 1.5 or whatever, then I'm going to find a third linear approximation. We're going to change direction again, so pick this up again at the step size, and we're just going to kind of follow that curve up again. Okay, so what I want you to do is I want you to find the third approximation, solve for y on your own, see what you get. So pause the video, do the last one, and then pick it back up. Okay, so we previously already found our new y value, and then we evaluated the slope at the new point, which is right here, and then solved for y to get our final answer. Okay, so this is just kind of the basic idea behind Euler's method. So what he did is he came up with this method to evaluate. So if I, again, have a differential equation and I want to know the value of another point, then you can use what's called Euler's method. So this is the basic idea, but he came up with a nice, neat formula for us, which is called now Euler's method. So I want us to write this down. So if we are interested in just one specific y value, so in the past example, we were wanting to evaluate what y of 1 is. So we're going to call that y sub n, and that's going to equal the previous y, which would be y sub n minus 1. Okay, and that's kind of what we did here. We had to go back to the previous y and the step size plus, okay, next is our step size. Our step size has to be involved somehow. So that's going to be h, our step size. And then that step size is going to be multiplied by, and remember this notation that we showed you in the last video with slope fields. We have this capital F of x sub n minus 1, y sub n minus 1. And all that represents, that capital F there, is our differential equation. And the n minus 1 means we know our previous point, so it's calculating that derivative, that slope at the previous point. All right, you can kind of see the pattern there. That's what we just did 3 times in a row for those linear approximations. So let's just make sure we understand. So I'm going to call y sub n like our new y value. And so then the n minus 1 would be the previous y value. The h is our step size. And then this whole thing right here is our differential equation. So that's dy dx for our slope, evaluated at previous x and y. Okay? All right, so that is Euler's method. And this is something that you're going to have to memorize. but it's actually really not that bad. So now we're going to do two examples of applying Euler's method. Okay, so looking at this example, and you see that I've written Euler's method up at the top, so I can follow that through here. They give us the step size. So sometimes they'll give us the step size, and sometimes they'll give us an interval, and we have to calculate the step size. So we have step size of 0.2, and we want to estimate y of 1. Okay, so what is our y value, or an approximation of our y value when x is 1, where y of x is the solution of the initial value problem. So that's just saying this is our differential equation, and our initial value is given at the point 0, 1. Okay, so with Euler's method, they're going to have to give you a point. Okay, you can't do Euler's method unless you have a point. So what I typically do with Euler's method is I make a big table, so an x, y, t chart. Okay, and we know that our initial x is at 0 and our initial y is at 1. And actually, that's the same exact information that we were given with the last video notes, and also with this first example, we're looking at x plus y and seeing what's happening. So we're trying to estimate what that y value is right here. So we've already done this with a step size of 0.5, and we got this 2.5. Okay, we already estimated that to be 2.5. So now with this example that we're doing, we are using a step size of 0.2, so we should get a better approximation. All right. So our next x value, if we use a step size of 0.2, then our next x value would be our previous x value plus that 0.2, so we're at 0.2. Then we'd have 0.4, 0.6, 0.8, and we continue on in that step size until we get the x value that we want, which here is 1. Okay? All right, so now what we're going to do is for each of these x values, we're going to calculate Euler's method by doing the process that we've already talked about. So what that would mean is I would take the previous y value, so for 0.2, the previous y value, so that's this y and minus 1. The previous y value is 1, plus the step size is 0.2, times our derivative calculated at the previous x and y. So our derivative is x plus y. So all I'm going to do is simply add my previous x and y as 0 plus 1. Okay? So we'll go through that each step here. Hopefully by the end you'll feel pretty confident. So a lot of times I do end up using a calculator for Euler's method. This one's pretty straightforward, though. You can do this one without a calculator for a little bit at least. So that's going to be 1.2. So then now to do the next step size, we use the previous y value of 1.2 plus the step size times the derivative evaluated at the new x and y value. So, or the previous x and y value, which is 0.2 is the previous x value plus the previous y is 1.2. So again, if you use your calculator here, if you need it, you would get 1.48. Okay, continuing on at 0.6, previous y plus step size times previous slope is 0.4 plus 1.48. And we get 1.856. Okay, a couple more times, previous y plus step size times derivative evaluated at previous point. And we get 2.3472. And finally, we are at our final thing, so previous y plus step size evaluated, or derivative evaluated at previous point. And we finally get this evaluation. Okay? So that is an even better approximation. If you go back and look at our graph, we said that this y value was 2.5. So 2.9 is going to be maybe up in here, and you can see you get a much closer approximation, less of an error there. Okay? So now what I want you to do is, we've been dealing with the same differential equation over and over again, the x plus y. So I want you to try the second example by yourself, but I want you to make sure and remember that your derivative is not x plus y this time. Okay? So keep that in mind, but you're still going to do previous y plus the step size times the derivative, whatever that is, which changes, evaluated the previous x and y. So again, I want you to pause the video. I want you to get out your calculators if you need it, and I want you to find or solve example 2. Okay, so there's the answer for example 2. So look over that, make sure your answer matches line. So hopefully that makes sense with Euler's method, and we'll practice in class.